Hi everybody, and welcome to Theorem 2.23. We are looking at page 69 of the workbook. And up to this point in the section, we've been talking about the change of coordinate matrix, a matrix that allows us to change between one set of coordinates to another. And this theorem extends this discussion to the question of, if we've got two different coordinate systems out there, could we compare the matrices of a linear transformation relative to these two coordinate systems? Okay, so let's start reading this theorem together. So they start us off by saying, let T be a linear operator on a finite dimensional vector space. Now, I'm not sure that we've used this term before, linear operator. That's just a word for a linear transformation that has the same domain and codomain. Okay, so in our case, it's a linear transformation from V to itself. Okay, and then continuing with that sentence, let beta and beta prime be ordered bases for V. And suppose that Q is the change of coordinate matrix that changes beta prime coordinates into beta coordinates, same matrix that we've been talking about. Okay, and then the theorem tells us this, equation star, that the matrix of T relative to beta prime is equal to Q inverse times the matrix of T relative to beta times Q. So it gives us an equation that relates the matrix of T relative to these two coordinate systems. Okay, now what's kind of nice here is that without formally proving this theorem, we can conceptually arrive at equation star through a diagram. Okay, we can kind of work our way naturally to that formula. Okay, so looking down at the bottom of the page here, we've got a diagram that they've sort of started for us, and I'd like to see if we can complete it by filling in some of the pieces. Okay, let's start with the arrow that we see kind of in the middle of the diagram. So to go from V to T of V, we would apply the transformation T. Okay, and I'd like to see if we can kind of think about the other two arrows in a similar way. Okay, so up here, what would take us from the coordinate vector of V relative to beta prime to the coordinate vector of T of V relative to beta prime? If you think back to what we did earlier in this chapter, it would be multiplication by the matrix of T relative to beta prime that does that. That's exactly the meaning of that matrix. And then similarly down here, there, if we multiply by the matrix of T relative to beta, that would take us from V beta to T of V beta. Okay, and I'd like to add two other things to our diagram here. Okay, first thing would be to notice, what would it require to go from the coordinate vector of V relative to beta prime to the coordinate vector of V relative to beta? If you think about that, we're changing coordinates from beta prime to beta. That's exactly what this matrix Q is, okay, in words. And so multiplication by Q would take us from there to there. And similarly, if we go the other way, if we want to go from beta coordinates to beta prime coordinates, we could multiply by the inverse of Q. Okay, so we have a complete diagram now, and I'd like to think through how that diagram can help us to come up with this equation star, okay, that we're looking at. Okay, so basically we can get that equation by thinking of this as being our starting point and this as being our ending point, going from V beta prime to T of V beta prime. One way to do it is to take the high short road and just go via this matrix, multiply by the matrix of T relative to beta prime. That's the left-hand side of this equation. But there's another way to get from here to here in our diagram. We could take the low road and first multiply by Q, then multiply by the matrix of T relative to beta, and then multiply by Q inverse. So Q, T beta, Q inverse. Notice that if you look at the right-hand side and read it backwards, Q, T beta, and Q inverse. Now, why do we read from right to left there? Okay, well, here's one way to think about it. Suppose you were to take that matrix and multiply it by a vector. Okay, I'll just call it X. If you did that multiplication, what would get multiplied first? Okay, the q would get multiplied by x first, and then you would get that result, and then multiply t beta on the left by qx, and then finally by q inverse. So that's why we read from right to left. That's the correct order to read in, okay, due to the fact that that's the way we multiply by a vector. All right, so our diagram led us kind of in a natural way to this formula that we have here. All right, and one last piece that I'd like to throw in that's kind of convenient. Sometimes it's nice, instead of having a formula for t beta prime, to have a formula for t beta. So I'd like to write down a second formula that goes with this, and we can reason this out by thinking of this as being our starting point and this as being our ending point. The short road from here to there would be just to take and multiply by the matrix of t relative to beta. That's this left-hand side. What if we took the long way, okay, from here to here? Well, we would start out maybe by going like this. That's going in the opposite direction of q, so that would be q inverse. Then we'd multiply by the matrix of t relative to beta prime, and then finally we would go back down to here. That's going in the opposite direction of q inverse, so that would be q. And if we put those together, q inverse t beta followed by q, that's what we need to write, and we're going to write it in the reverse order again. So q inverse t beta prime and q. That's what belongs in our blank. Let me see if I can write that a little bit neater for you here. T beta prime and q inverse. Okay, and again, we haven't proved this theorem, okay? But we've given some pretty good conceptual evidence that it seems reasonable that it should be true by drawing this diagram, okay? And in the next videos, we'll do some examples showing how this theorem can be useful to us.